Well, welcome to our DMSC tenure talk. So we're going to have a talk from Professor Raf Jaramillo, who is not going to tell us just about his scientific discoveries, but he's going to tell us about the path he took to come here. And the idea is to give our grad students, undergrads, our junior faculty, an idea of some of the things that take place as you go forward looking for tenure, rather than we don't just sit in our offices writing papers. There's just a huge number of interesting things that we have to do, and also uninteresting things. And there's a lot of coincidences and synergies and good luck and bad luck. And really, it's something of a random walk, I think. And the idea is that you know where you want to get to, you're here, but do you go in a straight line? No, there are barriers, there are saddle points, there are chasms that you fall into and you can't get out of for quite a long time. So the hope is that by showing everyone how this process works, we might inspire particularly some of our younger colleagues and students to think about the academic life in a little bit of a different way. So that's the motivation for these talks. I want to be, I don't want to talk too long, but let me just introduce Raf. Raf is actually a physicist by training. He has degrees from Cornell, and he has a PhD from University of Chicago. And then he did a postdoc in Harvard and worked in MIT before joining the faculty here in 2015. So he's also a survivor of the whole COVID pandemic academic venture. Anyway, let me stop now and hand over to you.
This has been a lot of fun putting these slides together. Now it's on. Great. Good? All right. So this is the talk title and the representative image that I gave to Jason and Nina, but I'm sorry, Jason and Nina, it was a red herring. So why did I do that? This picture was taken in April 2017. That's now 7 years ago. I'm 2 years into the tenure clock. I'm sitting in a puddle of leaked propylene glycol in my lab, trying to fix this bleeping chiller, and I'll give some of my students sort of like PTSD with these details, and we still have no films from the bleeping MBE, right? So this is really, with this in mind, and with all due respect to Ms. Swift, I want to present the real title of my talk, which is The Errors Tour, right? And what we're going to do is walk through all of the mistakes, small, large, catastrophic, and just funny, that brought me to this place today, right? Okay, so let's do it. I sort of gave away the game there with that bucket, which I think Kate Reedy is responsible. She's not here, but I think Kate Reedy hung that from my office door like a couple of days ago. It's like she knew. Yeah, she didn't know, but yeah. Okay, so like Taylor, I was born in the 1980s, just barely. And during this time period of 1998 to 2003, I was an undergrad at Cornell in applied physics. It's a lovely place to go to school. It's beautiful, even in winter. You can see it's very beautiful. I was an applied physicist, and I really wanted to work in industry on semiconductors or something related to electronic materials. At that time, the internet wasn't quite firing on all cylinders as a place to find a job. And even more than today, we relied on undergrad career fairs. This was a bigger deal then because you would actually get to meet people. And it's an even bigger deal when you're stuck in Ithaca, right? So career fair is a big deal. My senior year career fair ended up being scheduled less than a week after this event. And if you think we're living through uncertain times now, let me tell you, at least I think it was nothing compared to then. So there were two employers there, sad employers, both working from national labs, looking for physicists who could do some defense work, and I wasn't interested in that. So we all said, okay, what am I going to do with my career? So I stayed for a master's, a one-year thing, and I worked on computational plasma magnetohydrodynamics, which was a topic I was interested in because I had some interest in fusion energy. So it's still lovely, but you could see a little, sometimes at some point you get sick of trudging through the snow and you want to move on. So I was dreaming. I said, okay, this has been nice, but it's time to go learn something about semiconductors and electronic materials. I was dreaming of going to Berkeley. And I was admitted to Berkeley, and I thought this was fantastic. I'm going to go to Berkeley. And there was just one problem, which is that my girlfriend was going to Chicago. And so I wanted to go to Berkeley, and my girlfriend was going to Chicago. So what did I choose? Right? More snow. So followed the girl, went to Chicago. And Chicago is a great place, right? University of Chicago is a great school, except there's sort of a problem with it, which is that, they had no engineering school. I mean, now they do. They have an engineering institute, but I think those of us who have worked with them know they're still very fundamental, very molecular sciences. That didn't even exist then. It was, what did exist were these T-shirts, and you could buy these shirts then at the bookstore. And I've been back recently, and I've looked to try to buy the T-shirt, and they don't sell them anymore. And the moral of the story, there's one thing I want to tell you, is that if you're in life and you see a great T-shirt, buy that T-shirt, because you never know when it's not going to be available for sale. This is that's all well and good in practice, but how does it work in theory, right? I mean, I love Chicago. It's a great place, but it couldn't be less like MIT, right? So you end up doing some fundamental things. It all worked out well. We have these three, we've now been married for close to 18 years, and we have these three ridiculous kids. And let me tell you, it is raising kids while going through tenure at MIT, trying to get tenure at MIT, is very convenient. And it's convenient because when you have to travel to go give a talk or something, they can lecture for you. So it's a very convenient thing, having kids while getting tenure. So what did I do in Chicago? Okay, here's the first project. I thought, oh, this is great. I'm going to work on antiferromagnetism. That was the topic. And I saw that there would be some tremendous opportunity in antiferromagnetic spintronics. This would be the future. I didn't know how long it would take, but I thought it would be good to do some work in this space. And so we were measuring the Hall coefficient of chromium metal. Chromium is an elemental antiferromagnet of some interest because it also has spin and charge density waves and so forth. And within the first year, I was measuring these very, interesting data. I mean, yeah, they're ugly. It's noisy, but this is first year kind of stuff. And what we found is these hysteresis loops in the Hall coefficient. I'm not going to get too detailed here, but basically the point is that these features in the data opened at the Néel transition and closed at a spin flop temperature. So in between these two magnetic transitions in chromium, there is this hysteresis in the data. And the hysteresis depended on the sign or the direction of the current. And it depended even on sample polishing. And we started to think, okay, we're pinning domain walls and we're seeing some sort of skew scattering from the domain walls. And if this were ferromagnets, perhaps we could understand it, but it's antiferromagnets, so it's new, and we're very excited about this. And so, as a second-year PhD student, I had an accepted abstract to talk at the March meeting. I'm off to fame and fortune, right? Okay, March meeting, March 21st, that's Monday, right? Email, March 18th, that's Friday. Hi, Tom. I'm very unhappy to tell you that the temperature hysteresis loops may be false. Last night, I ran a scan on the MPMS designed to test the sample temperature stability, and based on the results, I could construct a rather simple explanation for the hysteresis loops, yada, yada. It came down to the fact that the temperature control sensor was at a point that was underdamped, but the sample temperature location was overdamped. And so the temperature, the time dependence of the sample temperature had the opposite sign as what I thought it had. And this explained all of the data. And it was all an artifact. So it's Friday. I canceled my trip. I love this email. 4-4. I want to make sure that I'm getting my money back. So I faxed a cancellation to their office. Can I get a refund on my March meeting? This is great. All right. So back to the drawing board. Oh my goodness. All right. It did end well, but it took a fair amount more work. 2007, right? So now 2 years past this. I went all the way back to the drawing board, had to redesign the measurements, redefine what we were going after, and in the end did, get real results published in PRL. So all's well that ends well. All right. What was my actual thesis work? This was sort of a warm-up. My actual thesis work was this effort. So Dennis McWan and Maurice Rice might be known to some of the old-timers here. I don't know. Dennis McWan ended his career at Lincoln Lab. In the 1960s, they had studied the pressure dependence of the magnetic phase transition in chromium. And their pressure cells hadn't gone farther than about 86 kilobar. And that's where they left it. But by the time my work came along, there was a lot of interest in antiferromagnetic quantum phase transitions. So a material which is susceptible to antiferromagnetism in the presence of quantum fluctuations was thought to give rise to anomalous superconductivity. And this is inspired by high TC and Coop rates and so forth. So we wanted to go over here, where, you know, if basically it was Herbie-Dragon's territory. And this was my PhD work. So we developed a lot of high pressure experimentation. This is some sort of stylistic images of circles, which are all coming from parts of diamond anvil cell experiments, synchrotron storage rings, and so forth. So, you know, this was all very good and fun. Here's another circle. But here's one of my favorite errors from that time. Okay, so I went off to Switzerland with some chromium vanadium samples to measure the magnetic order under pressure using neutron scattering. And here's the lab notebook. Heinrich Ronau is now a professor, full professor at EPFL. Christian Rüegg is a full professor at ETH, actually now director of the PSI. I don't remember who over. This guy here is speaking to you at the moment. So, but at that point, we were just clowns, right? Sure. And we're trying to measure pressure-dependent magnetism. We have this sort of capillary cell. So the sample sits down here. And this is a scan from my lab notebook. So I've noted it's 1-to-1, right, on the lab notebook, so I know what size things are. There's a capillary here that feeds the sample volume. And the capillary is fed by a giant compressor at room temperature on a big manifold. So there's a big old manifold with a compressor and a helium capillary. And here's the thing. My esteemed colleagues had driven down from Stuttgart, from a Max Planck at Stuttgart, which is a big place. They had driven this thing down. They had rented a truck with small wheels. I ended up looking at the truck because it becomes relevant. They had rented a small wheeled truck, put this pressure apparatus on, and driven down. This thing leaked like a sieve by the time it got down and hooked up to the beamline. This thing was, okay, so pump like mad. Crap. Back the same as before. Capillary is likely to have frozen before cell volume. So our big approach was to, on the beamline, have me with the hand pump. That's actually a video of me at that time. It's funny, we didn't have phones on us, but someone had a camcorder, and that's actually a video of me. And the idea is we would try to pump, while we crash the temperature down and try to freeze the helium in the capillary, so we'd freeze it in the high pressure in the cell. We're above the freezing point of helium, so, you know, helium has a unary phase diagram, so there is frozen helium. It's sort of like an icy plug. And so we'd crash the thing down as quickly as we could, get that icy plug, keep the sample pressure kind of stored, get the data, and the plug would disappear and we'd lose our pressure and so forth. And if you don't believe me that that's me, here's a picture of me from that time. Another picture sort of in repose, right, in a relaxed moment in a hutch. And so you can see that, yeah, that is actually a video of me from that time. All's well that ends well. We published many works on this project as a whole. This trip to Switzerland ended up, it was like these 12 data points. It's like an inset, right, sort of off of, which, I found it interesting actually. You're measuring a dimension on the Fermi surface as a function of pressure, temperature, and doping is what you're doing when you measure these spin and charge density wave ordering vectors. We did more, right? Not just the pressure cell. We did a lot of diamond anvil cell experiments. This was a data set I was particularly proud of, showing the charge density wave order parameter crashing over about 4 orders of magnitude according to an exponential form. This is a weak coupling model, so it's like a BCS superconductivity model, until it finally crashes down to the critical point. And then we were able to do a lot of experimentation looking at that quantum critical point. It was a lot of fun. Published many papers, including this one in Nature. We were all excited about ourselves at that time. And if there's one thing I have to say, it is I'm embarrassed of the title. I didn't say it at the time. I've never told Tom I was embarrassed of the title. But breakdown of the Bardeen-Cooper-Schrieffer ground state. It's just the same equation. It's not the same thing. It's not a superconductor. I don't know how all these old guys let me get it, or I don't know how we let ourselves do that. So don't embarrass yourself. All right, but otherwise, it was a success. So, okay, fine. Finally, I was at Chicago all this time. It's time to find a postdoc and learn about semiconductors, right? So I made a list. I still have the spreadsheet. So I was able to look back. And these are some of the names at MIT. So I'm going to work for these people. And Angie Belcher had given a seminar in physics at Chicago recently, like prior to this. And I thought everything she said was just cooler than the last thing she said. I said, that's who I want to be when I grow up. Like, And so I emailed Paula, because Paula and Edgy were on the same project, on August 5th. I love this. Then I waited. And then I emailed them on November 7th, right? And then I waited some more, and I emailed on December 2nd. And what's not noted here, but it's true, is I then started calling. I leave them. Probably they don't check their voicemail. Probably if they check their voicemail today, I still might be on there, right? Hello, this is Raphael Jaramillo. I think if I had continued on, right, if I had continued at that pace, I would still be looking for a postdoc, I think, right? Sort of. So this is great. I did end up moving to Harvard. I did many things at Harvard. This is really the silliest thing that we did. Among other things, I said, well, I was at the Rollin Institute, and I said, okay, at that time, 2010, 2009, there was a major controversy in quantum dot optoelectronics, which was the source of blinking. So quantum dots would emit intermittently. And it was known to have something to do with statistics of something, but the something was unknown. And the idea of how to control it to get more uniform light emission from quantum dots was a big problem. And I said, no, I'm going to solve this problem. I'm going to solve this problem using an old STM that it was moved from Bell. It hadn't been used since it was moved from Bell. And really poor synthesis control. That's what I'm going to do, right? And that was an error, but not for the reasons you might think. So this is the reason why it was an error. It turns out that East Cambridge has the shakes. Did you know this? Who knew this? I also knew that. So this is my geophone data, October 2010. The geophone, in the vertical geophone and the horizontal geophone, on the floor and on the air legs that were supporting this multi-chamber UHV STM. And you can see it's horrible. Not only is it horrible, there's this 2 hertz vibration which is amplified by the air legs. And if you go to Newport or whatnot and you look up the spec sheet of air legs, they amplify below like 3 hertz, right? They don't damp, they amplify. So worst case scenario. And in fact, then we did some digging and found out Jennifer Hoffman, who's a professor of physics now at Harvard, her PhD thesis at Cornell, I mean, she knew this. She had somehow, for the appendix of her thesis, surveyed all of the geophone data from all these scanning tunneling microscope labs around the country. Obviously, she's at Cornell, so they're boasting about how much better their lab is than everywhere else. But there's MIT, right? So it was known. MIT was bad. East Cambridge. And someone told me that, I read, actually, this is a lot of reading. Can we solve this problem? The one thing to do would be to buy active vibration isolation. But this project basically had no funding. I mean, we were, so those tables are expensive. So that wasn't an option. Another thing I learned is that granular media is good at damping low frequencies. So I went to Petco. Jim's going to love this because there used to be a Petco on First across from the mall, right? It's not there anymore. Now it's like a condo. There used to be a Petco First across from the mall, which is near Roland. So I went over there and I bought a bag of kitty litter and I put the geophones on it, and sure enough, it damps to 2 hertz. So unfortunately, this was a multi-chamber UHV STM. There's no way I could, just put it on a bed of sand, right? The project had no funding. I was in a room, basically. No one cared or knew that I was there doing this. So it died, although I will say, look at this. They're very sensitive to 2 hertz noise. This is why they use the litter box. They're very comfortable during their business. So all's well that ends well. We ended up realizing that because of this noise, we couldn't do tunneling because the tip couldn't be held within angstroms controllably of the surface because it was bouncing back and forth with like a 10 to 15 angstrom oscillation. So you can't do STM under those circumstances. But we tried to make the best of it, and we ended up doing what I thought was a very interesting series of experiments on cathodoluminescence. So we couldn't do STM, but we could still inject charge locally with a nanometer or sub-nanometer resolution, and we can inject electrons and holes, whereas normally cathodoluminescence, you're only injecting electrons because you have an electron column, right? There's no hole column in an SEM or STM. So it was quite nice, I think. We were able to sort of look at the polar dependence of a single defect, we thought, or defect cluster. Luminescence, right? We sort of map these on the surface of a sample. So, you make lemonade. Okay. I spent another postdoc in Tonio's group here, and I'm very grateful for that time. I learned a lot. I'm not going to go over, there were no errors made. So now it was time to become a professor. And here's when I discovered, through empirical experimentation, the power law rule of faculty applications. Right? So here's the power law rule of faculty applications. You have on the order of 100 applications, on the order of 10 interviews, and on the order of 1 offers, right? Here you have it. So, anyway, having discovered that physical law, I received this exciting email from the Department of Material Science and Engineering. We have reviewed the material in light of the needs of our department and have decided not to pursue your application further. I would like to thank you for your interest in MIT. All right, so that was received 6:32 p.m. So I took the body blow, right? Who knows, got a beer or something. And then at 10:20, I was like, okay, I'm ready to write. Dear, I'm really sorry to hear this. Thank you for the timely note. If there's any feedback from the process you could give me, right? And went to bed, despondent. 5:52 a.m. Your case is still very much alive. There is a continuing discussion in which you remain a top candidate. This email was automatically generated by another person. So the sender here is still one of my colleagues, so he gets blacked out. But these two folks, they no longer are, so I don't mind saying, So what an ordeal. Anyway, so I got the job. And now what am I supposed to do, right? Now I got the job. What on earth? So I did many things. I mean, we built a group up around taking chalcogenide materials processing as a strategy, right? And there's much to say on that. And I could have given a talk about that, but I chose not to give a talk about the group strategy. We could talk about that later if folks are interested in sort of pursuing this kind of a path. I do, however, want to highlight one of our projects. I love all my children equally. But I'm highlighting this one because it really has been the longest and most difficult road, right, which fits in the theme of this talk. So let's talk about why make perovskite chalcogenides. So the idea is to start with complex oxide crystal structures and replace the oxygen with sulfur or selenium. This ought to lower the band gap by 309(1) arguments, basically solid state chemistry. While retaining what I found at that time to be really rich science, where you have a blend of covalent and ionic bonding. See, I'd been working on complex oxides and late transition metal complex oxides, specifically nickelates, as a postdoc. And I spent a lot of time thinking about, what makes nickel and copper oxides different, and it's the fact that they're fairly covalent with respect to oxygen. That's what makes them so interesting. And I thought this is an interesting direction to push farther. Let's turn that up to 11 and see what happens, was my thinking. And, this was expected to, be like a semiconductor invention kind of strategy. But in other words, John Goodenough told me to do it. I don't want to pretend I overthought this. I basically did what he said. When I was a postdoc, I did a lot of reading because when I graduated with my PhD, I didn't know the bandgap of silicon. I mean, I was working on quantum magnetism. I knew nothing. And so I needed to do a lot of reading to try to catch up with the people around me. And one of the best things I read, one of the most influential things I've ever read, was this. It's not a paper, it's practically a book. It's about a 100-page article by John Goodenough. Now, I had known John Goodenough because of the Goodenough-Kanamori rules for magnetism. But, this is telling you how full. I didn't know he was in material science. I didn't know. And so this is really John holding my hand, saying, this is how you can stop being a physicist, take advantage of some things you know, but this is how you can start being a material scientist. And he has a wonderful exposition here where he develops these phenomenological theories that capture a lot of this transition from ionic to covalent bonding, which you would call from correlated to uncorrelated systems. Really beautifully written, And so thank you. I mean, he's no longer with us, but I really am indebted. So I mentioned John Goodenough in the abstract. That was not a red herring. I really did want to highlight him. And I just couldn't help myself. I Googled it. I mean, he's about to conquer the world, right? As a student at Chicago. We're used to him in old age because he lived so long. But it's really amazing to see this picture, I suppose, from the World War II times, right? Yeah. Anyway, John Goodenough is not a red herring. So why chalcogenide perovskites? Let's look back here. Started digging into this. They have a wide range of theoretically predicted band gaps. The y-axis here are DFT, LDA level sorts of calculations. So you take it with a grain of salt. The abscissa is really just like ordering these by band gap, by prediction, right? So it's a series of compounds. And the colors are meant to be suggestive of the wide range of band gaps. And so if you look at this, it's sort of like a treasure map. At the time when our collaborator, Jay Ramachandran, and I wrote this sort of review paper, it's really a perspective, there had only been 1, 2, 3, 4, 5 compounds that had been made and with their band gaps measured. But they were close to the theory predicted values. That's what those black dots are, which says, okay, this really is a useful treasure map, right, for finding new semiconductors. But at the same time, it's not really obvious that they'll form. right? Because this is theory, and you could put the atoms where you like them, relax them a little, and figure out what the band gap will be. Andrew Rapp, who had been doing some early theory work in this space, had written a couple careful papers studying the structure field maps and making predictions for stable crystal structures. This has come a long way in the last 10 years, but this is forefront stuff from maybe 10, 15 years ago. And the point of this is that there are no perovskites predicted stable in this chemical space. I don't want to get into the details, but these are all lower dimensional structures, which may be interesting, but not good for semiconductor applications. However, nature preferred to make perovskites, actually. It turned out that there's a discrepancy between what was predicted by DFT and what actually forms. And we continue to find these discrepancies. Those are fun. It was known that this is a distorted perovskite structure, this gadolinium ferrite, or it's an orthorhombic corner-sharing perovskite, and you can make sulfides with that structure. In fact, going back into the Soviet literature, in 1957 is the earliest paper I could find, and you can make them. So, it had been made at this, sort of when we took off this effort. I would say that there is several generations of history of making these materials, right? So this was the context. There's, powders in crystallography, early powder synthesis. And then I would say with the advent of halide perovskite solar cells, there's sort of a renewed global interest in anything that has the word perovskite in it. And so you find a new wave of works where people are making these phases, mostly by solid-state synthesis. Some work again by Jay Ravichandran, my sort of friend and collaborator there, demonstrating single crystals, and then a slew of groups in recent years making thin films that are, low quality, let's say, but thin films nonetheless, where you get the right phase. But they look like this, and you're never going to make a high-performing device out of a semiconductor that looks like that in SEM. So what's next, right? So we decided to, do what's next, and our approach was gas source chalcogenide MBE, which is really making our lives as difficult as possible. But the strategy there is to try to establish what high-quality material would perform like, right? And work backwards from there. And there's also a bit of technique development, which makes the sort of work I like to do. So, we bought this, this company shortly afterwards went into liquidation and was bankrupt. It no longer exists. So, I don't know what that says, but we bought an MBE, sort of a cheapo MBE. We have a fusion cells for barium and tin. That's how we supply barium. We have an electron beam evaporator for the high melting point, low vapor pressure metals. We use these gases, hydrogen sulfide and hydrogen selenide, which we continue to evolve forward our use of those gases. And we also have plasma sources for those gases, which is quite a rare asset. We don't use those so much yet. We push forward one of the theses which will come out of my group in a few years will be to replace the E-beam with metal organic, and we'll talk about why. And I think of this as like, chalcogenide gas source MBE actually has a rich legacy. Leslie Kolodjetsky in the 80s was working on this. There's a lot of work in Japan in the late 80s, early 90s, because before the Nobel Prize winning work on GaN, there was the 2,6s that were thought to be in the material that was going to be the future of solid state lighting. So you see a lot of gas source MBE work, and it just ends. It's like 1992. There was like an apocalypse, and all the gas source chalcogenide MBEs were wiped off the face of the earth, and you don't find another publication. So I was reaching out to these old Japanese guys who didn't get back to me. So we're sort of like reviving this as a method for new materials, right? Which brings me back to my picture of sitting in a puddle of propylene glycol next to a not working chiller across a wall from a not working MBE. So let's talk about all the things that could go wrong with an MBE. In fact, MBE, right, stands for mostly broken equipment, which kind of implies that at some point it worked. But that was never even, we started from what's less than zero. Even when you buy an MBE today for a legacy established material system, let's say 3 nitrides, 3 5s, from a company that exists, that sells these into production, like Vico or Rebair, you still expect broken equipment. And here we bought this MBE on the cheap for a material which never existed, for chemistry that had never been put together before, by somebody that, by the way, had never done epitaxy, never done MBE. I remember I was doing diamond anvil cell stuff, right? So this is basically what ensued. I could go on and on and on. I want to show you just some of the funny highlights. Here's a really detailed thing, but it matters a lot. The issue of gas purity. Now, if I had had a background in MOCVD, metal organic chemical vapor deposition, I would have known this, like in my bones. But I didn't have a background in MOCVD, so I hadn't appreciated the need to purify the gases, not just buy the most pure gases I could buy, but purify them right at the point of application. It turns out to be terribly important for reasons which are often unknown. You just want to solve the problem, you don't want to necessarily understand it, right? You just want pure. Here, residual gas analyzer data, January 2018. We're really getting up there in the years, right? I mean, that tenure clock is now on year, 5, 6, 7, 8, 3, moving on. When we turn on the H2S, we get the H2O, right? You cannot make chalcogenides this way. Hydrogen sulfide and hydrogen selenide are really weak reducing agents. They have a really weak reducing potential. They will not pull oxygen from anything. They definitely won't pull oxygen from zirconium oxide. Zirconium is a hard cation, oxygen is a hard anion. They are going to find each other, and you are not going to pull them. You can do it with carbon, but short of carbon, you're not going to do it. You're definitely not going to do it with hydrogen sulfide and hydrogen selenide. Oxygen is a poison, and we had it in spades. And so, I mean, this was like a year-plus long effort to figure out why this was, and nothing was coming out of my lab from this effort. Fortunately, we were doing other science, but nothing was coming, right? My whole startup and then some poured into like this giant black hole. So I taped all the lines in the lab for baking out. I said, oh, it's the stainless steel, it still had water in it from installation. Let's bake it out, right? Nothing. What ended up solving the problem is we said, okay, let's throw the kitchen sink at this. I can't go systematically and identify the problem. I'll be out of the business if I do it that way. Let's do a bunch of things at once. So the first thing we did was we redesigned our gas delivery system. Those are proximity injectors, 1, 2, 3, 5 little EDM drilled holes in injectors which spray hydrogen sulfide and hydrogen selenide right at the sample. So it's like a garden soaker hose of death. We added point of use purifiers, which turned out to be just common sense in hindsight, but I hadn't known to do that. And we also redesigned our gas injecting system to use a higher grade of mass flow controllers, because I strongly suspect still, I would bet a cup of coffee, that the elastomers used for safety reasons were slowly leaking oxygen into my process. And that was reacting with some of the hydrogen from the hydrogen sulfide and hydrogen selenide forming water. And that's what was poisoning the growth. I don't know if that's true. And I'm okay going to my grave not knowing if that was true. We just solved the problem. And here's some more problems, just for fun. Okay, do you see that end there and that end there? You see how they're not connected? So the E-beam uses high power leads in vacuum, so it's copper. But because we're using chalcogenide, right? Chalcogenide, copper loving, that's what that word means. Hydrogen sulfide will react with copper. You need to like scrub copper from the inside of your system. And so we have nickel plating everywhere. But if a nickel plating fails and just a little, this was a manufacturing failure because we hadn't opened it up at this point. The thing corrodes, the thing Joule heats, runs away. And what you get is a puddle of high power lead, sort of like somewhere in the bottom of your chamber, which is, it's really, the chemistry is really amazing. Error. There's also building 13 conditions. There's so much that could be said about building 13 conditions. And I wouldn't make this subject of this talk except for one of my favorite pictures that was ever taken in my lab. Adriana was is a fantastic student. She was visiting us from HCB in Berlin. And in Berlin, they do things carefully and well, right? They don't have situations like building 13 in HCB. And she found the conditions in our lab just so comical, right? So we have our own air handler. On the outside of the building are ledges, right? On the ledges are pigeons. And the air handler is so good at filtering that we get feathers. So that is not the first time and not the last time that we found pigeon feathers on the floor of the lab. And for her, this was, what are we doing? So the error is not her. Adriana is fantastic. The error is, MIT. It's MIT, right? It's typical MIT stuff. But fortunately, we'd solved those problems, and those were uneventful, worry-free years, right? So that's an error. Fortunately, in the Jaramillo group, we were well prepared for COVID because we work on toxic gases, and we wore masks before it was cool. So we were ready for this. We were ready for anything. It did end well, and it continues. So this is a beautiful data set. I use this. In fact, I use this as the whole poster one. So I just printed it out and showed it. This is Jim's data, Jim and Michael, right? This is STEM showing epitaxy of a chalcogenide perovskite on an oxide perovskite, right? After we had solved all the problems and the pigeons and the gases and everything, right, we get the growth. It actually works, and it allows us to do a lot. So the first paper, the author, one of the reviewers, we had said mirror smooth, and they said it doesn't look mirror smooth. I said, well, yeah, it's because of the lighting of the picture. So I went and I took this picture, which demonstrates that the film was mirror smooth. And then Ida thought that was sort of fun. So at a later point, we were going wafer scale. She sent me this picture. So we have these beautiful pictures of mirror smooth films, right? You see flowers reflected in the films, right? These are thin films on substrates, and they're atomically smooth, as we know from other measurements. But you can reflect flowers in them. We've done things like map out the band gap across an entire composition series from the sulfide to the selenide. I mean, this is all new. It also, I think, puts us on the map in the sense of starting to think of these materials the way that legacy semiconductors can be thought of. This is something called the Cho plot by the inventor, or one of the co-inventors of MBE, Al Cho, showing the band gap versus lattice constant for semiconducting compounds. And it's where you start designing a device, right? You go to the Cho plot and you think about what sort of device you're going to make based on that. And I sort of had dreamed of putting these materials on this plot through epitaxy, and so we've done it. We don't have devices and technologies yet, but this is sort of the realization of a partial vision. The blue band there is kind of where you need to get to for thin film PV, single junction. So we're sort of selenium alloying getting down there. These are all first. And now, for example, we have these 2-inch wafers. I love these pictures. This is the sulfide. It's got a 1.9 EV band gap, so it appears nice and orange. We can push it, to high selenium, even all the way content, pushing down the band gap into the optimal range for single junction PV, still with very nice uniformity across a wafer scale. Where is this heading into the future? A couple notes on that. What is the outlook for these particular materials? I feel like as if I'm repeating myself because I hit some of these points about an hour and a half ago in a group meeting. Thin film PV is an advanced manufacturing approach, which is important for competitiveness. It is an unlimited renewable energy resource, and it has very short carbon and energy payback times relative to wafer scale photovoltaics or solar cells. But the whole sector is in trouble. It's in deep doo-doo. We could talk about why, but the numbers sort of bear it out. This is the percentage of sales by technology class going up to about 2022. And thin film PV had its heyday about, back when I was at MIT Sports Day Camp as an 8-year-old, and has only been losing market share since then. And there's lots of reasons for this, but basically every particular thin film technology you look at has a limited, what do you call it? A runway, because you don't take off, like just a track that ends. I'm not sure. And so, you say, are these the savior materials, right? Is this the material that's going to really revive thin film PV as a contributor, right, to low carbon power? There's certainly a lot of review papers that think so. I mean, these things come out. I don't read them, basically. I mean, I would say that, my advice to myself and what I hope my students get is ignore the chatter, right? Keep your eyes on the horizon and focus on improving synthesis and processing, right? I'm not going to worry about all that yet, right? Let's get the materials, make them better, make them better, make them better again. And there's lots of steps, which I'm excited about. There's not time for here to discuss. I will say, just for fun, because I'm really excited about this, and I've only talked about the chalcogенide perovskite so far, but we're doing a lot else in the group, and I'm going to highlight only one, which is Olivia's project, which is really extremely different. Right, so I don't know how many people here follow the field of superconductivity, but if you look here at the critical temperature of superconductors by year, you have, the original sort of discovery of superconductivity by Cameron Ioannis when he first liquefies helium and then enables the discoveries. And then I think niobium may be the first, I don't remember. Anyway, and these are called conventional superconductors. And then there are the high TCs, right? Sort of 1980s heyday of high TC, cupriate high TC. And then there were iron-based superconductors. And now all the record transition temperatures are held by materials that are made and tested at very high pressures. So it's a little bit of like what's old is new again for me, because I have this background in high pressure physics, but I don't want to do high pressure physics, right? I want to try to make ultra high temperature superconductors as stable room temperature thin films, right? Ambient condition thin films, right? So that's the goal. So how are we going to do it? We're going to do it by combining a couple of things, which seem straightforward. First of which is chalcogenide, epitaxial growth of chalcogenide superconductors. to stabilize otherwise unstable phases. The second is doing this in H2S, so developing the electrochemistry and the acid-base chemistry of hydrogen sulfide. Because we're doing this in H2S, we have to do this in the condensed phase, and which means we have to go down below the boiling point of H2S, which means we have to do it at some ambient. So we're going to we're combining, where we are, we have, this is going ahead, chalcogенide superconductor epitaxy, H2S acid-base electrochemistry, and cryoelectrochemistry. So I'll ask you, what could go wrong, right? All right, so I want to end by thanking, my group members, present and past. I wish everyone could be here. Colleagues and collaborators and friends and family, of course. And I'll leave it there.